Okay, today I will talk about statistics and their distributions. But before I explain what is a statistic, let me tell you something about what a population is and the characteristics of a population. A population is a universe of items, and very often the characteristics of that population are not known to us unless we have data from a complete census study of the population. These characteristics of the population are known as parameters, which are constants for that particular population. These parameters are often required and are not known. So, what we do is we take sample surveys which are really examination of small subsets of the population, and then try to assess the properties of the population from the sample information. This objective will be best served if the sample taken from the population is a representative sample. There are many methods available for us which we can use depending on the nature of the population, the kind of sampling method we use. But a sample therefore, that we collect from the population is a subset of the population. We can study the sample data and use that to estimate or make predictions about the population parameters. What is a statistic? A statistic or estimator is a combination of sample values. Now, since a sample is a subset of a population and a very small subset, it is very unlikely if we examine two different samples of the same size taken from the same population using the same method of sampling, it is very unlikely that all the units that are in the first sample would be repeated in the second sample. There are always going to be a lot of differences between the two samples. Therefore, when we talk about a statistic which is a linear combination, an example of is the mean of the sample. What is the mean of the sample? The arithmetic mean. The arithmetic mean of the sample is taken by just adding up all the sample values and dividing by the sample size. Since we are having the sum of the sample values, and if the sample values themselves are differing from one sample to another, then naturally the mean of the sample will be different from one sample to another. That is why we say the sample mean is a random variable. If you compare with the population parameter, with the population mean, that is not a random variable, because that is a constant. In fact, all parameters are constants for the population. They may vary from population to population, but even though we are taking the different samples of the same size using the same method from the same sample, because the sample values vary from one sample to another, any combination of the sample values, which is known as a sample statistic or estimator, will also vary from sample to sample. Therefore, as I said, the sample statistic is a random variable. For any random variable, we can find a probability distribution from that variable. The probability distribution of a statistic is referred to as a sampling distribution of the statistic. So, for example, again, if we were going to take a large number of samples from the same population and calculated the sample mean from each and every one of those samples, we will get a distribution of the sample means, and this distribution will be the sampling distribution of means. So, what kind of sampling distribution we will get for any statistic will depend on three things. Number one, the type of population from which we are taking the samples. Okay. Number two, the sample size, and number 3, the method used for sampling. Although there are several methods, the most commonly used method is that of simple random sampling. The reason simple random sampling is so popular with researchers is that if samples are drawn with this method of sampling, then it becomes much simpler to arrive at the probability distribution of the statistic. Let us see what a simple random sampling method is and what is a simple random sample. A simple random sample is defined by 2 qualities. One, that each and every sample unit that is drawn is independent of the other units. That second, that each and every unit has an identical distribution. So, that is why we say that the sample units are independently and identically distributed. What does it mean? Now, let us say we are taking samples from a population, with population is distributed with a mean value of mu and a variance of sigma squared. I am not mentioning anything yet about the form of the population, I am just mentioning the parameter values are mu and variance. Therefore, in the population each of these xi's in the population are distributed with the mean mu and variance sigma squared. When you take a simple random sample, let us take the first unit, sample is of size n. Now, when you draw the first unit, it could be any one of the population units, it could be any one of the population units. Now, within the population, the first unit has a particular probability of occurrence in the population, second unit has some other probability of occurrence in the population, so on and so forth. So, when we draw this unit, it could be any one of the population units with their respective probabilities. Therefore, the first unit of the sample, let us call it x1, will also be distributed like the population with a mean mu and variance sigma squared. Now, according to the random sampling technique, each and every unit are independently and identically distributed. Therefore, the second unit x2 is independent of x1 and has the same distribution as x1. So, that too will be having a distribution with mean mu and variance sigma square. So, right up to the nth unit, all of them will have the same distribution mu with the mean mu and variance sigma squared. Which means for a sample of n units n1, x1, x2 to xn, with each of these xi's are distributed with the mean mu, that means expected value of xi is equal to mu, okay, and variance of xi is equal to sigma squared. What is the mean? X bar is equal to sum of xi, where assuming there are n units in the sample divided by the total number of sample units, this is x bar, that is a statistic. It is a linear combination of all the sample values. Expected value of x bar will then be expected value of this whole sigma xi upon n. By rules of mathematical expectation, 1 upon n is a constant, will come outside. So, we have 1 upon n expected value of summation xi. Now, that means expected value of x1 plus x2 plus x3 till xn, which is nothing but the sum of the expected values. So, we have 1 upon n summation I from 1 to n e of x I, that then you get 1 upon n. Each of these x i's is distributed with a mean mu. So, so it will be mu plus mu plus mu plus mu n number of times, n times mu, you are left with mu. So, what do we find? If the population from which the sample has been drawn has a mean value of mu, then the distribution of sample means will be centered at the same value mu. Expected value of x bar equal to mu means that if you were to draw a diagram to represent the distribution of sample means, then we are measuring x bar over here, and whatever may be the form of the distribution, I have not yet talked about that, but you will get a lot of x bars having different values because they are from different samples. Some of the samples may have picked up some very high values from the population. It is a matter of pure chance which units got selected. Then you get a higher value of x bar, the other some will be having lower values of x bar, and then there will be all the others. And when you look at the mean of this distribution, the mean of this distribution is mu. In other words, the expected value of x bar or the mean of the sampling distribution of x bar will be the same as the mean of the population. Now, for any distribution, whether it is a population distribution or a sampling distribution, besides to the mean, you would also like to find the measure of the spread of the distribution, which is the variance of the distribution. So, let us see what is the variance of x bar. Variance of x bar is again equal to variance of summation from I equal to 1 to n x I upon n. So, now here there is equal to sigma x I upon n. For again rules of mathematical expectation, according to that you can take out 1 upon n squared, because 1 upon n is a constant, and variance of a x is a squared times variance of x. So, a being 1 upon n squared comes outside, and you have the variance of the sum of x I summed over I. We have made the assumption that the x i's are independent. Because of that assumption, this actually becomes 1 upon n squared summation variance of x I, because there are no covariance terms, you have this. Therefore, this now is equal to sigma variance of x I. We have already shown that each of the sample units has the same variance sigma squared, and there are n such units. So, this becomes n times sigma squared. So, sigma upon variance sigma squared upon n. Now, we have learnt a lot about the sampling distribution of the statistic x bar. We can similarly find out the sampling distribution of some other statistic. One such statistic could be the sample variance, where the sample variance s squared is measured as summation x I minus x bar squared divided by n minus 1. That is how we define the sample variance. And similarly, you can try to find the distribution of sample median, of some percentile of the, so on there any of the statistics which are of interest, trim mean, many other statistics are there. Here, when we have used that assumption that the xi's are independent and identically distributed, in that case is an unsaid assumption we have made, because right from the beginning I am saying that each and every of the x's must be having equal chance of getting selected, but that is what the simple random sampling method leads me to state. But these x1, x2, x3, x4, etc. will be independent and identically distributed only if sampling is with replacement from, if it is a finite population, or if the population is infinitely large, then also these conditions hold. In fact, the conditions for having a simple random sample, that means the two conditions of the xi's being identically and independently distributed, holds exactly if sampling is from an infinite population or it is with replacement from a finite population. In that case, the probability of the kth unit being selected from the population is not affected by what units have been selected before, which is what we mean by independence also. And also the probability of selection of any unit is not affected by how many units or which units were selected prior to that unit. However, if sampling is without replacement, which means a unit has been chosen from the population and not returned to the population before the next unit is chosen. In that case, if it is a finite population and the sample is large, in that case with every draw from the population, the number of units left in the population is being depleted, and the probability of selection of the next unit is affected by what has been selected in the previous draw. However, even if sampling is without replacement, but the sample is small relative to the size of the population, okay, we say at most it should be 5% of the population size. So, let us use n capital letter to denote the size of the population if it is a finite population, and we are using small case letter n to denote the sample size. All right. Now, if n is okay, that means we say n the sample is small relative to the population. In that case, the probability of any one unit being selected is not that much affected, because we can continue to take sample units without really exhausting the population. So, in those cases, what we said earlier, that xi's are independent, identically distributed, those conditions are not exactly met, but are approximately met. It would be interesting to know at this stage what are the number of samples you can draw from a population. Of course, if the population is infinitely large, in that case you can go on taking any number of samples from the population, because the population does not get exhausted. In case the population is finite and sampling is with replacement, then let us see what happens. Sample is being drawn from a finite population. The first unit of the sample could have been selected in any one of the n ways. It could have been the first or the second or third or nth unit of the population. So, the first sample unit could have been selected in any of the n ways. Now, this is with replacement. So, unit goes back, the population remains unchanged, the population does not change after each draw. So, when you select the next unit, that can also be selected in n possible ways. So, like that n number of times. So, the total number of samples that you can get will actually be given by n n. Total number of samples that you will be able to draw will be n raised to the power of n, which is theoretically quite a large number, almost infinitely large. So, it is quite a big number. On the other hand, if sampling is without replacement, then the total number of samples that you can draw is given by NCN. Okay. So, as I said, if sampling is with replacement from a finite population, we get n raised to the power of n possible samples, which is quite a large number, and if it is without replacement, these are the NCN number of samples. So, that the probability of selecting any one sample becomes 1 upon n raised to the power of n in this case, and 1 upon NCN in this case. So, you get a probability of a sample, but remember, whatever may be the probability of the sample, for all the samples taken from that population, the probability remains the same, whether the first sample has this probability, the second, because once a sample has been collected and the observations are made, all the units are put back in the population. So, the population again goes back to its original form, even if sampling is without replacement. Let us take the help of an example and see the relationship between the characteristics of the distribution of sample means and that for the population. Okay. Let us take values 2, 6 and 10. This is the population values, very unrealistic, but it is for the illustration purpose only. So, these are the population values given to you. The mean of this distribution mu, we normally use the Greek alphabets to denote the population parameters. So, mu is for the mean of the population. This is therefore 2 plus 6 plus 10 upon 3, which works out to 6. Similarly, the variance of the population sigma squared, we can write it as which is sigma xi minus mu squared upon n. So, that becomes 4 squared is 16 plus 0 plus, have I got it right? Yeah, upon 3. So, that is 32 divided by 3, 10, 1, 6, 6, 7. So, please remember mu is 6, or I can write on the top, mu is equal to 6 and variance is equal to 10.667. Now, let us say we take samples of size 2 from this population and sampling is with replacement. Then the total number of samples we can obtain are n is 3 raised to the power of 2. So, which is 9 samples when samples of size 2 are taken with replacement from the population. So, first sample unit, second sample unit. I set up a table of all possible combinations. Now, when you have sampling with replacement, the order in which the units are selected from the population is not relevant. So, let us see the different possible combinations. There should be 9 such samples. Let us, first is 2, the second could be, or let us say second could be 2, first 2, second could be 6, first 2, second could be 10, again first could be 6, second could be 2, 6, 6, 6, 10, I am running out of space, 10, 2, 10, 6, 10, 10. So, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 samples as to be expected. For each sample, I can find the mean. Mean of this sample is 4, mean of this is 8, 4 divided by 2. 1 minute. Okay. So, this mean will be 2 plus 2, 4 divided by 2. This is 2, this is 8 by 2, which is 4, 12 by 2 is 6. Similarly, 8 by 2 will be 4, 12 by 2 will be 6, 16 by 2 is 8, 12 by 2 is 6, then again 16 by 2 is 8, and the last one will be 10. From this we can set up the distribution for x bar, where x bar takes these possible values 2, 4, 6, 8, 10. Total number of samples are 9, 2 occurs only once. So, probability for x bar over here will be 1 upon 9. 4 occurs 2 times only. So, 2 upon 9 is the probability of 4. 6, 1, 2, 3 times. So, this is 3 upon 9. 8 occurs 2 times, 2 upon 9, and similarly. Thus, we can obtain the probability distribution of x bar. Now, this is a very small example to show how it can be done, but normally the populations are large, and trying to obtain the sampling distribution by repeated sampling becomes a big exercise. Then it may not be worthwhile. One of the main reasons why we use sample data instead of taking a census to find out about the characteristics of the population is census being a large exercise sometimes is impractical. Even if it was possible, it becomes expensive, very costly in terms of time and money. So, if we were to do this whole this experiment of drawing repeated samples, we will be again using up a lot of time and money. Without that, how do we find out about the sampling distribution? I will come to that shortly, but let us finish studying what we have learned. We have a distribution sample means. The moment you have a distribution, you can find out what is the mean of that distribution. So, therefore, expected value of x bar would be summation whatever value you get from your, where I now is the ith sample, the first sample, second sample and so on, the sample value multiplied by the probability of x bar I, where I is here ranging from 1 to 9, the 9 samples. So, this would be 2 times 1 upon 9 plus 4 times 2 upon 9 plus 6 times 3 upon 9 plus 8 times 2 upon 9 plus 10 times 1 upon 9. When you complete all the calculations, you will find that 2 plus 8 plus 18 plus 16 plus 10, you will get again the expected value will work out to 6. So, therefore, mu x bar is equal to 6, which is also the population mean. The mean of the sampling distribution is equal to the mean of the population. In other words, the distribution of the sample means is centered at the value which is corresponding to the mean of the population. This property will always hold regardless of the form of the population. I did not make any assumptions about the form of the population. I just stated that the population is distributed with a mean value of mu, which in this case happens to be 10.667. So, this is a property of the statistic x bar, that the distribution of x bars will always be centered at the mean of the population. Now, this is a very useful property. In fact, when we use the sampling distribution, there are two kinds of uses that are mainly for inference theory, for estimation, for tests of hypothesis. Now, x bar is used as a point estimator of the population parameter value, because it is an unbiased estimator. Though this is not the only possible unbiased estimator, but x bar has additional properties besides to being unbiased. And how do you show it is unbiased? When you can show that expected value of x bar is equal to mu, which I have already shown you the algebraic proof earlier on. Now, I have also can show you what is the variance of this particular distribution of sample means. To calculate the variance of x bar, this is equal to expected value of x bar squared minus expected value of x bar the whole squared. For expected value x bar squared, you have to take the sum of the squares. So, 4 upon 9 plus 16 twos are 32 upon 9 plus 36 into 3, let me 64 into 2 is 128 upon 9 plus 100 upon 9. So, this becomes 32 plus 4, I have got the calculations done, so I will have a quick look. So, this becomes, this is 108. So, this becomes 41.33 . This was of course minus 36 from here. So, minus 36, this works out to 5.33. Now, comparing this value with this value is a very interesting thing. This is approximately equal to the population variance divided by 2, which is nothing but the population variance divided by the sample size. Therefore, the sampling distribution means is not only centered at the population mean, but the variance of the distribution is the population variance divided by the sample size, and therefore, the standard deviation of x bar will be sigma divided by root n. This is the result we are getting from here, and it can be also shown. Earlier I had shown what is the variance, take the square root of that, you get sigma upon root n as the standard error or the standard deviation of the distribution of means. This of course is under the assumption that sampling is with replacement. This will hold, but in case sampling is without replacement from a finite population, then although the mean of the distribution still remains mu, we have to add a finite population correction factor to get the variance of the sampling distribution. In case sampling without replacement from a finite population, then sigma squared, that the variance of the distribution x bar will be sigma squared by n multiplied by n minus n upon n minus 1. This is n minus n upon n minus 1 is known as the finite population correction factor or FPC, and in that, and this will be therefore equal to sigma upon root n square root of n minus n upon n minus 1. Now, note, although we apply this FPC, in case the sample is very small relative to the population size, then what happens? As the sample size falls relative to the population size, your n minus n upon n minus 1 tends to 1. This ratio becomes closer to 1. As n becomes smaller and smaller fraction of the population size, n minus n upon n minus 1, that fraction, the population correction factor, approaches unity, and in that case this sigma x bar will approach sigma upon root n, which is the case when sampling is with replacement. Now, there is some two things we have already found out about the sampling distribution, that the mean of the distribution is same as the population, but the variance of the sampling distribution is not equal to the variance of the population. In fact, it is much less, whereas for the population the variance is sigma squared and it is upon n. As the sample size goes on increasing, the variance of the sampling distribution will also be decreasing. Let us draw a diagram and okay. Then so this is the sampling distribution of x bar for a sample size say n1. The moment you to change the sample size and do the whole exercise again and pick up fresh samples with a sample size n2, which is more than n1, in that case the sigma squared upon n2 will be less than sigma squared upon n1. The variance becomes less, which means the spread of the distribution becomes less, and you will have another distribution with sorry. You will have another distribution with again the same mean, but it will be closer clustered closer to mu. This is even the earlier distribution with a smaller sample size, that also will be a much smaller spread than the original population. The reason being is that when you are taking sample means you are averaging out the sample values, that negates some of the variability in the data, the result of which is that the x bar distribution will always be narrower than the original population distribution, only on account of the averaging out process when we are calculating the means. So, now we know two characteristics of the distribution of x bar, that is the mean of the distribution as well as the spread or variance of the distribution. That brings us to another characteristic, which is the form of the distribution. Three things I have already told you, these are the factors which are going to affect the distribution of any statistic. One was the population, the form of the population. Second, sample size. Third, method of sampling. We have used random sampling method, where all the units are independent identically distributed. We have fixed the sample size at n, and I have shown you how changing the sample size affects the sampling distribution, how increasing the sample size reduce the variability of the data. One more thing we have not brought into the conversation as yet is the form of the distribution. So, let us examine what will be the form of the sampling distribution if the population is normally distributed. So, we are making the assumption that the population distribution is normal with mean view variance sigma squared. If the population is normally distributed, then each of these sample units x 1, x 2 right up to x n, all the sample units, each one of them will be a normally distributed variable with mean view and variance sigma squared, each of them. So, each of these xi's would be normally distributed with mean mu and variance sigma squared. And what is x bar? X bar is nothing but a linear combination of all these normally distributed random variables. A linear combination of random variables which are normally distributed must also itself be normally distributed. Therefore, we get x bar is also distributed normally. We already found out what the mean and variance are. So, this will be distributed with mean mu and variance sigma squared by n. Okay. But all populations are not normal. What happens if the population is not normally distributed, or at least we do not know that it is normally distributed? So, what happens in the general case where we cannot assume that the population is normally distributed? In that case, we take the help of one very important theorem in statistics. It is known as the central limit theorem. According to the central limit theorem, it says that if the sample size is sufficiently large, in that case the distribution of sampling means will be approximately normal with mean mu and variance sigma squared by n. Closer the population is to our normal distribution, smaller needs to be the sample size, greater the divergence of the population from which the samples are being drawn from a normal distribution, larger has to be the sample size. Okay. It is considered that if the variance of the population is known, that means sigma squared is known, in that case if sample size is at least 30. So, if sigma known, then n is at least 30. In that case, x bar will be approximately normally distributed. X bar will be approximately normally distributed, even though the population may not be normally distributed. If the population is normally distributed, then x bar, because x bar is a linear combination of our normally distributed variables, is also normally distributed. But if the population is not normally distributed, in that case x bar is a linear combination of xi's which are not normally distributed. But the central limit theorem shows us that even if each of the individual xi's are not normally distributed, because we are taking a sufficiently large sample size, the averaging takes place. As a result, the distribution of sample means is more bell shaped than the parent population from which the samples have been collected. That is the contribution of the central limit theorem. Here I assume sigma squared is known. Supposing sigma squared is also known, which is quite possibly the case. If mu is not known, sigma squared may not be known. If sigma squared is unknown, then we need to estimate sigma squared again using sample data. So, then we use sample variance x squared summation x I minus x bar squared upon n minus 1 to estimate the variance. So, then when you are using an estimate of the variance, in that case we have to have a larger sample size where n must at least be greater than or equal to 40. Then also we will have x bar to be approximately normal. The practical difficulty is knowing what is the appropriate sample size. There are cases like in the case of the uniform distribution is not normal distribution at all, although it is a symmetric distribution. There even a sample size of 12 gives you a normal distribution for the sample means, whereas there may be other distributions where you need a sample size of maybe 50 or 60 or even more, but those cases are rare. Mostly we find that if you have samples of 30 or in this case around 40 or above, you are able to approximate a normal distribution for x bar. So, basically CLT or the central limit theorem provides a shortcut. If the sample size is sufficiently large, we can simply go ahead and approximate the distribution of x bar by the normal distribution. If we can assume x bar to be approximately normal, then it helps us in the kind of work that we normally use this for. A lot of work is done to draw conclusions about the population, whether it is estimation or test of hypothesis, where we require knowledge about the distribution of the sample mean. Now, if you were to set up a sampling distribution by taking samples repeatedly, that becomes a huge exercise. So, there are analytical methods which can be used to obtain sampling distributions. One is with the help of rules of probability. And secondly, with the help of simulation experiments. Again, let us use the example of the which we had just now, the population we had of 2, 6 and 10. I will show you how rules of probability can be used to obtain the distribution of sample means. In either of these cases, to be able to show what the distribution of the mean is going to be like, we need to know what the population is. Now, rules of probability to obtain sampling distributions is possible when you know about the probability of each of the units in the population, which you can apply. So, here let us assume that the probability of to be at 2, 6 and 10. Let us say the probability of 2 is equal to 0.2, probability of 6 is equal to 0.5 and probability of 10 is equal to 0.3. Let us assume this is the probability distribution of the population. Given these, now we are drawing the samples. Again, we would be able to draw different samples, the 9 different samples we would have been able to draw. And again, remember that any one of those value x's could be any one of these, but once you have selected the samples, that particular sample, then the probability of the whole sample is a joint probability of all the units in the sample. For example, if the first sample is 2, 2, x1 is 2, x2 is 2, both are 2, and we have the probability of obtaining 2 as a first unit is 0.2, and that of the second unit is also 0.2. So, you get 0.4. Okay. The probability of the sample is, there is a, sorry, there is a 0.04. 0.2 times 0.2 get 0.04. The probability of the sample is the product of the probabilities of each and every unit in the sample. Similarly, if another sample you had one unit was 6 and the other was 10, the product of these two would be 0.5 times 0.3, which is 0.15. So, we can do this analytically if we know what the population probability distribution is, and from there we can obtain the distribution. Now, only over here the form of the population must be known, or at least it should be a and the statistic that we are studying should also have a more or less a simple kind of formula. Then it's an alternative to using rules of probability is what are known as simulation experiments, where you use computers. Now, for these experiments, certain conditions have or characteristics of the experiment have to be set up in advance. Number one, the statistic of interest, whether it is a sample mean or sample variance or any other characteristic of the that we are studying. So, statistic of interest has to be specified in advance. Secondly, the form of the population and their parameters. So, population and parameters, the characteristic must be known. So, whether if it is normally distributed with a mean mu naught or and variance sigma naught squared, where there is a uniform distribution with the lower limit alpha and the upper limit beta, this should be specified in advance. Number 3, of course, the sample size, which is n, and fourth thing is the number of replications of the experiment. We denote as k, number of times the experiment is going to be conducted. Now, we use of course a computer program to generate samples repeatedly. That means, k number of times samples are drawn under the assumption that population has a certain characteristic. That means, the form of the population, the parameters are known. Sample size of course is fixed in advance of the experiment, k is also fixed in advance, and then again if we are, I am using the sample mean as an example. So, here we can set up the distribution for the sample mean through this exercise. So, if there are k number of replications, there will be k such sample means. Normally, if the statistic under study has a simple form, in that case 500 replication, 1000 replications are good enough to give us the sampling distribution. Once we have obtained the different k x bar values, then these can be placed in we can draw a histogram, and this histogram actually is nothing but a representation of the sampling distribution of x bar. It is an approximation to the sampling distribution. As your number of replications increase, you get closer and closer to the real sampling distribution. As they say, when if k becomes infinitely large, as it becomes infinitely, the histogram will be giving you the sampling distribution x bar. We can draw a curve and for the histogram, and that will give me the curve for the sampling distribution, will approximate like that. So, these are the two analytical methods One is as a rules of probability, where you can all the different samples. I gave examples of only 2 of them. The 9 samples you can drop over there. You can find the probability distribution by simply the products of the individual units in each sample. And the alternative is this, of course, the method is mostly used if it is too complicated or difficult to obtain the distribution with the help of rules of probability. In that case, we use the simulation experiments, and you will find that as your k increases over here, as said, your sampling distribution will approach a normal curve if the original population is normal. So, once you know how to obtain the sampling distributions and you know the characteristics, one is, as I told you, the form of the distribution, which with the help of CLT, even if the population is not normally distributed, if the population is the sample is sufficiently large, you can assume x bar to be at least approximately normally distributed. You have the mean of the distribution, you have the variance of the distribution. Once you have these, then we can use x bar in the study of the population. As I said, there are 2 kinds of studies we have. Both are decision problems. One is to estimate the value of the unknown parameter. Secondly is to test whether a specific value of the parameter can be accepted or not. So, for both these kinds of studies, a knowledge of the sampling distribution is required. In case of the population mean, because we have already seen that the expected value of x bar is equal to mu, we in fact that is a condition for unbiasedness. So, x bar in fact is an unbiased estimator of mu. It is used as a point estimator for mu. We can even set up what are known as interval estimates, we give a range of values again centered at the sample mean, and again we use sample mean again for your test of hypothesis, because we can standardize it. Z that we get as a standard normal distribution, we can use the Z table to be able to test for hypothesis, but that is not part of today's topic. That will be some other day.
Ma'am, in the formula of sample variance, why do we divide by n minus 1 instead of simply n, which is the sample size?
Well, answer to your question, Nihal, is why we are using xi minus x bar squared n minus 1 for sample variance. That is your question. Why not by n? When the total number of sample units is equal to n, why we are dividing by n minus 1, whereas in the case of mean we were dividing by n. Only in the case of variance we are dividing by n minus 1. The reason being is that these are the sample units xi. Now, if we were writing mu over here, that is a true population mean, then we would have taken sigma xi minus mu. If we had taken summation xi minus mu squared, then we would have divided by n, where the sample size is n. But since we do not have mu, we are first estimating mu with the help of the sample mean, because by definition the variance is the sum of the deviations of the values around the mean divided by the total number. So, around the mean, but we do not have mean, we are using the sample mean. We are losing one degree of freedom, we are having one restriction on the data. So, that is the reason we have to subtract by 1 to get the variance, simply because we have substituted x bar instead of mu.
Is central limit theorem applicable to discrete variables also?
Right. Now, the central limit theorem is applicable even if the population distribution is of a discrete variable. For example, if the population was a binomial distribution, that is a discrete variable, yet when you are taking the means of the for the different samples taken from the same binomial distribution, when you are taking the means and if the sample size is sufficiently large, in that case the distribution of the sample means approximates a normal distribution. That is a contribution of the central limit theorem.
Ma'am, just you said that there are a few cases where even if n is equal to 60 or more, then also CLT is not applicable. Ma'am, my question is that what is the practical significance of such a variation?
Right, I did say that. Now, I am putting the whole thing in perspective. There are also cases where you said that even for n equal to 12, like for the uniform distribution, we still get normal approximation to the distribution of x bar. Similarly, at the other end of the spectrum, there may be cases where you might be requiring a size of 50 or 60 to ensure that your distribution is normal. But those are very rare cases. Actually, CLT at no time gives you a specific value of the minimum sample size required. It has been found over a lot of work that has been done that mostly samples of 30 or 40 are able to cover most situations. There may be a few situations where the sample size may need to be more than 50 or 60 as I said, but those are very rare. That is actually why I said that is a practical difficulty also. We do not know for sure unless you know what the population is. If you knew what the population is, you would not need the CLT. But because we do not know what the population is, that is the reason we are requiring the central limit theorem to be able to understand what is the form of the distribution of sample means. And it has been observed that in most cases a sample size of 30 or 40 is adequate for our purpose, and that is why we have used it only as a rule of thumb. And we may be in fact using a sample larger also than what is required. Maybe a sample size of 20 would have been sufficient, but we do not know. We are using a sample size of 30 just because we do not know what the population is. It can go either way. We might be using a larger sample than what is actually required. We might be using a smaller sample than what is actually required. But since we have no way of knowing, we are just using this as a rule of thumb.